Good. Thank you. I'm Martin Herbordt, and this is Miriam Leeser, and we are very briefly going to tell you about the FPGA part of the Open Cloud Testbed. Since this is a very short talk, I think I'd just like to get across. Okay. I'd like to get across maybe just 2 points, and one is that FPGAs can go into lots and lots of places in the data center, and the second is that in each of these places there is a wide variety of capabilities. So with those two thoughts in mind, let me jump right into it. So first, motivation. Oran already talked about Microsoft and how 5 years ago Microsoft made the monumental decision, especially for those in the FPGA community, to put an FPGA into every new server to do all sorts of functions, which I'll talk about in a second. And Doug Berger has given this slide deck often, and this is his view of the world, and I guess perhaps ours too. And some of the things that they are using the FPGAs for are system uses, SDN, instrumentation, and so on, internal applications, compression, encryption, and also, amazingly enough, applications themselves that they sell as a service, most especially machine learning. In parallel to this, there have been various university research programs, including ours, where we've looked at not just the bump in the, turn it on, not just the bump in the wire out here, but also FPGAs in lots of different places, which again is the first message, that we have for a long time been using FPGAs as accelerators and even as accelerator clusters. For a long time, Mellanox has had FPGAs on NICs, and for a while, are coming back now, FPGAs in the router that are even programmable for things like low latency, well, for high frequency trading, low latency trading. Amazingly, in parallel to these parallel efforts, we have Intel, who has developed an entire new infrastructure called COPA for use in high-performance computing. And Venkat is here, and I'm sure he'd be happy to tell you more about his incredible project at Intel. So we have been going around conferences for a few years talking about how incredible it would be to be able to have these things, especially Catapult, but that is everything that the MOC is. A research test bed, well, open to people who are not working, an open test bed. And the FPGA part of this project, why do we need this? And well, as I just said, in Microsoft Catapult, we don't have user access. There are other systems where there are FPGAs available, most well-known AWS, which we all use, but these are really application platforms where we don't even have access to our hardware operating system development itself. Finally, there are a number of FPGA clusters that are developed at national labs and in academia, but again, these are hard to use, very difficult to make use of to outside, and also dominated by high-performance computing as an application. So just a quick view of some of the projects that people are doing in the data center. On the hardware side, Ahmed, in just a couple of minutes, will be talking about hardware operating system and development environment. There are also the system applications that we talked about, including privacy-preserving computation, and a whole bunch of other projects, each one of which has the order of magnitude speed-ups. Things like middleware acceleration, queue matching, other offloads. Lossy compression has turned out to be sort of an incredible application that HPC people desperately need. Massively parallel computations at the back end, and distributed machine learning, just for a few. And now I will turn it over to Miriam.
So, as Martin said, I'm Miriam Leeser from Northeastern. Both Martin and I have been working in FPGAs for a very long time, and so have a number of people in the audience. And it's just at a really exciting time to be in this area because FPGAs have become mainstream. Everybody's talking about them. So the goal of our project is, like Martin said, to make FPGAs available. We're still at the evaluation stage in terms of how and what that infrastructure is going to look like. We're hoping to get lots of input from the community, but we're really determined basically to have an open test bed that people can do really innovative things. And one of the challenges for us is how do we deliver that? How do we give people the things they want? And so part of that, and this is thanks to this NSF grant, we will be hiring a full-time FPGA engineer to work on some of this. We're integrating into everything you've heard about this morning, so existing infrastructure, which we think will help a lot. Most of the projects you've seen have been, certainly the academic ones, have been sort of one-off clusters and don't have that infrastructure. And then, like I said, the broader community is really essential to make this successful. So we're looking to all of you to make that happen. So to figure out what we should do, and like I said, we're still in our early planning stages, we went off and did a survey. So here's just a list of various universities who we surveyed. The X's are the people who responded, but we've been in this community for a while, so we went after what we consider to be like sort of the heavy users, as well as some people in labs, industries, et cetera, to try to figure out exactly what people want to see done with this. So, Martin and I are the alpha users, basically. And then once we get to beta stage, we'll be opening it up. And we're really hoping at this time next year, we'll have a really nice set of users. So we asked people what they wanted. And here's kind of an overview of different ways people want the FPGA connected. I would actually summarize this by saying that no one wants the latency that you get from being an attached accelerator to a processor, right? We want to be first-class citizens on the network. Whether or not that means doing research on the network, it does for a small set of people, but really what we want is very, easy access to FPGAs, straight off the network, very fast access to data, make the pipes direct, et cetera. Here's a list of the different projects. And the answer is people want to do things all over the map, from cloud and operating system research to middleware. I know a couple of people on the list are looking at various security issues, tenanted applications, just basically almost everything. So we had 17 responses, and everyone was really enthusiastic, but I think that's a self-selecting audience, right? The people who responded were very enthusiastic. We did ask of Intel versus Xilinx preferences, and it was pretty evenly split, which is kind of interesting. High bandwidth memory is a really hot thing in some of these server cards. Half of the respondents said yes, the others didn't really reply. I don't know if those are the people who've used it already or not. And then people, didn't really care that which board. They were much more wedded to sort of the tool flow that they were familiar with. So right now we're evaluating two different options. One is an Alveo card from Xilinx. I guess that came out a little smaller than I realized. It's the Alveo 280. And the other one is an Intel card. And each of them has its advantages and disadvantages, and each of it has its proponents, and we're actually getting both in-house. We have the Alveo card at Northeastern, we're getting the Intel card, and we'll be evaluating them and seeing what's going to be involved in setting these up. Here's a very quick summary. We'll talk more about this in the deep dive, but the Alveo card has high bandwidth memory. It has networking connections we could use, but only 2 of them. Intel has more of those connections, but doesn't have a high bandwidth memory. They each have essentially their own design flow because the tools come from the manufacturers. So those are the things we're looking at. And if you want to hear more about thoughts, directions, et cetera, our breakout session is tomorrow afternoon at 2 p.m. So please join us because we'd really like it to be a community discussion about where we go from here. So thank you.
Morning, folks. My name is Ahmed Sanaullah. I'm a senior data scientist at Red Hat. Sorry, change of roles. I keep confusing. I work on building an open source toolchain for FPGAs. There's a lot of wonderful people involved in the project. From Red Hat side, we have Uli Draper and Hugh Brock. We also have people working on this from the academia, such as Professor Martin, who was my PhD advisor till last year. And then also a lot of people from industry are working with us on this. So we've heard that FPGAs are being deployed in the cloud and in the edge, but that's part of the solution. We also need to be able to leverage these FPGAs effectively to truly benefit from them. And long story short, we need to be productive on these FPGAs. So what is productivity on FPGAs? Well, I like to define it very simply. Productivity on an FPGA is being able to deploy your workloads within the finite resources that you have on a chip, to do that in small time frames, and to do that with high performance. Where does productivity come from? Well, just like other technologies such as CPUs, productivity comes from the tool chain. Today, when you write CPU codes, you're just focusing on the application, and you let the tool chain figure out what's the best way to optimize this for the target architecture. Well, an FPGA tool chain, let me just get rid of the animations there. Right. An FPGA tool chain is quite similar to that of a CPU. You can start from a high-level language, such as C code, and using something called a high-level synthesis compiler, you can generate HDL code, which is the assembly language for FPGAs. You can do that either by taking vendor IP blocks and stitching them together to form your circuit, or if you're comfortable working in assembly directly, you can write your own library of components. And then you can, of course, do RTL simulations, which allow you to verify the functionality, to get estimates on performance before you actually spend hours and hours generating actual hardware. Once you're sure that's the design you want to take forward, you take that assembly code, and using a couple of processes, you generate the machine code, which we call bitstream. The first process is synthesis, where you convert the behavioral representation of hardware into a net list of gates and wires, connect them together. And then you do place and route, which basically takes this logical representation and maps that to physical resources on the FPGA. So for example, an FPGA doesn't actually have gates. It has lookup tables. So in order to implement a gate, you implement the functionality of that gate as entries in the lookup table. To be able to do this mapping, you need to know what the FPGA actually looks like, because every FPGA has differences in what is located and where is that located. So for that, you need access to that FPGA's database. Once you have a bitstream, you can push that out to the FPGA using a programmer. On the FPGA, you have a reconfigurable hardware operating system running, which does what an operating system should be doing. It multiplexes resources, isolates multiple users, et cetera, et cetera. And then you have a software runtime that allows that device to talk to host application, that allows managing of job queues. Again, what we expect a software runtime to do for external devices. The problem is that this has typically been proprietary. And there are many, many reasons why that's a bad thing. And you can think of this as any other software being proprietary. But let's look at 4 reasons here. 1, you can't customize. You're stuck with the functionality that you're given. And the alternative to that is either writing your own, which takes a really long time, or building in wrappers, which means you're going to consume more resources than you needed to get something working. Then there's licenses, and there's a lot of licenses for doing this. Sometimes you have licenses that are separate for different boards by the same vendor. Sometimes you have licenses that are separate for high-level synthesis versus just compiling HDL code to bitstream. Then rigidity of algorithms. Synthesis, placing route, for example, are core steps in generating hardware. You go from behavior to a physical implementation. But these steps have typically been proprietary. So you really just click a button and magically you have your design. You really don't have control over the algorithms, et cetera. And then finally, security. There's a lot of published work that talks about how having proprietary bit streams, not knowing what's actually getting pumped onto the FPGA, allows you to carry out side channel attacks, fault injections, exposes numerous attack surfaces. But we, in the past few years, have taken steps. No, we've taken strides in trying to address this problem. There's a lot of work being done to open source this tool chain. There's work being done right here in BU on, for example, the high-level synthesis compiler, where we're trying to build something that's fully open source, that does not require vendor IP to form these circuits by representing code in C. There's also work being done on Morpheus, which is the reconfigurable hardware operating system, where we're trying to have one operating system that can be deployed in the many configurations, the data center and the edge that you saw in the previous talk. Then we have work that we are doing with industry partners, such as Symbiotic EDA, who have built a synthesis and place and route tool set. It's not as good as vendors. You're within 20% performance of the vendors, but it is, steps taken in the right direction, and we hope for first closing that gap and possibly even going further beyond that. And then there's efforts done by the vendors themselves, the OPA software runtime from Intel and the Rapid Write tool from Xilinx. Rapid Write is basically Xilinx giving you access to the board database. You still need the vendor tools to compile the bit stream, but at least you can do your own synthesis and you can do your own place and route for their FPGAs. So in the last couple of minutes that I have, I'm going to do an example. This is something we did for my thesis. It's basically looking at high-level synthesis. Intel has this really nice tool, the Cl Sdk for FPGAs, where you write code in C and have that compile to hardware. We picked it up a couple of years back, and we thought, let's experiment with this. Let's see how good this really is. We got miserable performance. We followed the best practices guide to the letter. We did what we thought based on all the documentation out there that this is what you should be doing. And for an application that works well in FPGAs, if you code it in assembly language, we did not get good performance. But we knew that it wasn't the compiler, because the Intel engineers actually get good performance. We knew it was something that we were not doing right. There was a disconnect between what the compiler was expecting versus what we were giving it. And so we did the only logical thing. We hacked the toolchain. We instrumented the compiler. We made it spit out LLVM intermediate representations. We analyzed these, and we saw that, yes, the compiler is expecting code to be presented in a certain way so that it can extract the appropriate hardware primitives from it, and we're not giving it to it. And so we tried to take it this one step further and generalize the process, generalize the approach. Basically, we wrote a suite of probes that we run through a high-level synthesis compiler once. We take the intermediate representation data, we run it through a static profiler, and that tells us what the compiler wants to see for these basic FPGA designs that we want to build. For getting a SIMD out, for getting pipelining out, for doing caching in our hardware design. And then, taking the results of these profiler, we can then apply a set of systematic code transformations to our C code to actually then bridge that gap between us and what the compiler expects. And we actually got very good performance for it. We tried it for a bunch of network packet processing workloads. That worked really well. We tried it for a bunch of high performance computing workloads, and we got really good performance there. So what was so good about this? This was not a case where the algorithms were bad. This was not a case where the compiler was bad. But because it was proprietary, we just didn't know how to use it. There was not enough documentation out there for us to be able to actually leverage this important tool. But by being able to see under the hood, by being able to access all this intermediate representation, by being able to see what the compiler saw, we were able to actually improve our code structures. We were able to tell the right things, write the right code to be able to get this performance. And so that's my talk. Thank you so much for listening.
It's just right, this one here. All right.
Hi, my name is Anirban Mandal. I'm from RENCI at UNC Chapel Hill. Today I'll be talking about our work on leveraging distributed research cloud infrastructures for domain science research. So this is joint work with my colleagues at RENCI. Paul Ruth is here, with Eva Dillman's group at USC ISI. Michael Zink and Eric Leons are here. They're from UMass, and Ivan Rodero at Rutgers. So one of the major challenges for data-intensive applications is the integration of data into the whole scientific workflows that the scientists go through while doing the discovery of whatever process they're going through, right? So the challenge is how to move the data across diverse infrastructures, from instruments, from data repositories, into the computing platforms which actually do the analysis for the scientific tasks. How do you support complex workflows? How do you manage the elasticity of the requirements from the application side, the compute requirements, the storage requirements, the network requirements? So what we're doing in this work is we're developing some new algorithms and mechanisms that offer optimized data flows across diverse national cyber infrastructure resources. We're developing dynamic multi-cloud resource provisioning across Genie clouds, across NSF cloud resources like Chamberlain Cloud, XC resources like Jetstream clouds, and also we have done an initial integration with resources from the Massachusetts Open Cloud that we heard today morning. We're also developing a network-centric platform to bridge what we call as the abstraction gap. So it's really hard for scientists to use any of these advanced infrastructures connected through layer 2 networks, having multi-cloud distributed resources, right? So it's very hard for them to use them for their particular application use cases. So we are trying to develop a platform that bridges this abstraction gap so that it's easier for them to use the resources. We're also working on developing some data-aware scheduling algorithms so that we can map these applications effectively on these infrastructures. And we are deploying the solutions in the context of observational science use cases. And I'll be talking about one of them as a part of this talk. So for these applications, they express their requirements in the form of a Gantt chart, right? So they can express how much compute, storage, and network resources are needed for the application workflow at every point of time it's needed. And this Gantt chart abstraction is input into the network-centric platform that we call Mobius, which does the underlying resource provisioning across its multiple cloud resources, does the network orchestration by doing layer 2 network provisioning, and it exposes a REST API to the application and the workflows so that it's easy for the applications to actually provision the end-to-end infrastructure. So one of the applications that we're working on with Mike's group is the CASA application, which is called Collaborative and Adaptive Sensing of the Atmosphere. So traditionally, the high-power, long-range next-rad radars, they even though they're high-power and long-range, they have very limited ability to observe events which are closer to the ground, right? It's because of the Earth's curvature. So what the CASA radars do is, in the CASA system, they deploy a network of much smaller radars, but they can actually observe events which are closer to the ground, right? And there are 7 such radars deployed in the Dallas-Fort Worth area. So, and they can observe events like the hail, high winds, and tornadoes, which affect the society to a large extent. And another interesting thing about the smaller radars is based on the weather events that they observe. The weather analysis could drive the observation in a different way. It could turn the radar in a different way depending on the current observations. So as a part of this project, we ingest data from the CASA readers, and we have developed multiple of these CASA workflows, which do different kinds of weather simulations for responding to different kinds of weather events in the Dallas-Fort Worth area. The system that we deployed as a part of this project, which we call as the Dynamo project, is used operationally by the CASA scientists for real-time weather predictions. And this slide shows how we deployed a distributed research cloud for the CASA applications. We demonstrated this infrastructure at the Supercomputing Conference last year, where we used multiple research clouds from the Exogenie testbed, which is one of the Genie testbeds, and we have also used one of the NSF cloud testbeds, the Chameleon cloud sites. We brought the radar data to the show floor at SC, and we ran the simulation across these multiple cloud sites using dynamic multi-cloud provisioning with the Mobius system. So this slide shows the particular configuration that we used. This shows more of the details of the configuration. We use distributed testbeds, which are heterogeneous platforms. We use the hardware from Exogenie and Chameleon. We had the radar data repository at University of North Texas, and also a copy of that was on the show floor. And it shows the kind of integration that's actually required end-to-end for running these workflows in an operational sense. This shows a science example of a particular hail workflow that we executed using our system, where the CASA radar data were ingested from the radar data source, the radar data repository, into the execution platform across these multiple test beds, and we had the Pegasus workflow management system deploy these different applications on different parts of this multi-cloud infrastructure. And this workflow was run or was executed automatically on that infrastructure. And the figure on the right shows the output of the analysis, of the weather analysis that was done on the execution platform. It shows the orange contour shows the hail contour, and the red one is the wind contour. And this map actually is overlaid on actual physical infrastructures like hospitals and other important places, so that the emergency managers can use this output to avoid certain areas for emergency management. Currently, we're working on optimizing some of these data flows across multiple infrastructures. We're working on active monitoring and control. We're trying to support a larger federation of clouds, including Amazon EC2, Cloud Lab, and OCT. We're also working on data-aware workflow scheduling and deploying more CASA workflows, and we're also working on supporting streaming data. So that gives an overview of where we're going, and thank you.
All right, good morning. My name is Jonathan. This is Zhenpeng. We're PhD students here in the BU NIS Lab, and this morning we'd like to give a quick overview of some research that we've been doing related to strategic management in shared cloud services. So in a cloud market, you can have multiple different choices. The more traditional model would be purchasing resources from a single provider who's provisioning them. which of course is how the Googles and the Amazons of the world work. But you might also, say, be deploying OpenShift in an internal environment and then charge your users using the same model so that way they prevent the users from trying to oversubscribe and overwhelm the system by trying to claim all the resources for themselves. But in, say, between providers, you might have an open exchange model with an auction where providers or users who have spare capacity can then offer up resources, and then those who want the spare resources can then bid on them. But regardless of how your market is set up, what you ultimately have here is an interplay between engineering and management decisions, because you need to basically decide how you want things to work, and in particular, you want to prevent users from gaming the marketplace and distorting it so that way they benefit at the expense of everyone else. But in order to be able to set up a system to prevent that, we need to first understand how the users make the purchasing decisions in the first place. And we explored this through game theory.
Okay, so in the settings of game theory, we have the players, which could be the cloud users, and the potential providers. The providers could be the providers, a separate provider that operate the cloud, or the users themselves in the marketplace. So we want to reason about the strategies of these players. We want to find the best response against other players' actions. And what we are looking for eventually is an equilibrium, which is a state that no player wants to deviate from it. In other words, that each player is playing its own best response. So what's next after we know the existence of this equilibrium? We can characterize it from and understand the system from multiple aspects. For example, is this equilibrium unique? Is it stable? And from the provider's perspective, we can reason about the provider's revenue at a given equilibrium. And from the we can also look into the system social welfare, which is defined as utilities, the sum of the utilities of both the providers and the users. And in many cases, we may find that the social welfare is not optimal because the players in a game will assume that they are selfish, and so that may be a problem. So one key insight from our research is that it is possible to increase the revenue from the provider's perspective or the social welfare from the society's perspective, even if we do not invest in additional resources. And how are we able to do that? We can achieve that goal by judicious pricing and resource allocation, so that we can get the users to behave what we expect them to do, even if they only care about their own utilities. So next, we want to go a little deeper into our work and show what we found. The first one we want to talk about is the analysis of these shared buying computing systems. So in such a system, basically you have the shared users, which are like the free tier users of the cloud, and you have the buying users who own some computing nodes. And the decision in such a system is that we let the idle resources of these buying users to be accessible to all of the other users. So in such a form of sharing, the utilization of this system resources is enhanced, and everyone gets better off. So one takeaway from our analysis is that heavy users with large amount of workloads are in some sense subsidizing the light users, which seems not fair and may lead to the possible emergence of this free riders problem, which means that the heavy users may split their workloads and join the system as multiple light users without paying too much. A typical example of this shared buying computing system is the shared computing cluster at BU, which is located at MGH-PCC. So from this figure on the left, you can see how the SCC is widely used by the BU community. And the data from SCC show that this kind of sharing did enhance the utilization of this system. However, it is still not social optimal. So this figure on the right shows the number of the buy-in nodes owned by a product versus its total workload. And you can see that there are a lot of outliers which do not behave as what we expect them to do, and so which means that they are not incentivized well enough in such a system. So next question is there a better solution in terms of the social welfare? So for example, in the open cloud exchange model, we can consider implementing a decentralized marketplace in which we let the users themselves to allocate their resources through an auction mechanism, which could be a more efficient way of sharing if designed properly.
All right, so another thing we looked at is incorporating advanced reservation plus preemption into a system. So in this model that we looked at, we have the ability to basically be like a just-in-time user, like I need resources now, I will try and purchase them. But you might also be like, okay, well, I know I have a need for a large amount of resources 3 weeks from now when I run my experiment. I would like to be able to get a better chance of securing them. And so we allow them to get, or rather purchase an advanced reservation, and they would get priority over those just-in-time users. So we compared this to a system where there's no preemption whatsoever. Like you can still purchase that priority, but if once you're in service, you can't be kicked out. And a strict priority preemption where you purchase priority, but anyone with higher priority can kick you out even if you have a reservation. Under our model, if you have a reservation, once you're in service, you can't be kicked out. If you don't have a reservation, then you can be. But even if you aren't able to get in when you wanted, you still have priority over everyone who tried to make a reservation after you did. And we find that in comparing these models, the advanced reservation plus the preemption maximizes the revenue, as shown in this plot, where the green is the model that we studied, and then the blue is the no preemption whatsoever. And so, of course, the answer, or rather the question we want to ask is why? Well, the answer seems somewhat obvious. Users have incentive to avoid latency. Actually, the novel thing about this work is that under the model that we studied, the more people who make a reservation, the greater the incentive is for other people to do so, and that actually drives the cost customers are willing to pay higher. Whereas in the other models, the more people who do so, the less likely people who show up later will want to, because they're more likely to get preempted anyway, and so they're willing to pay a lower cost. But here, because purchasing allows users to avoid latency, they're willing to pay even more. And so one thing that we want to look at now then is, given what we know about this customer behavior, if we move towards a more auction-like system, if we permit advanced bids and give those priority over someone who tries to basically a just-in-time bid, how does that impact user behavior, and what mechanisms would need to be put in place in order to ensure that the mechanism isn't abused by someone who is trying to, say, hog all the resources, so I'm going to bid indefinitely into the future for everything that's available in order to get priority. So in summary, through game theory, we can understand these trends of user behavior in clouds. We can identify potential improvements through policy, and our future work includes applying these results to other market setups in order to see how those lessons translate and what else we can do to ensure the best benefit to all users. Thank you.
Where's your slide deck? Thought it was on already open. There you go.
Okay, good morning. I'm Daniele Buono, and this is a short presentation on the work we're doing in IBM research to improve the security of the Hypervisor. So why is this necessary? Well, the hypervisor is a very powerful piece of software because it's in charge of keeping a wall, an isolation between different virtual machines. So in theory, an attacker that is able to compromise the hypervisor could, in theory, get access to the host, or could also get access to virtual machines of other tenants. So this is why it's important to have an hypervisor that is as secure as possible. Now, in Linux, the hypervisor is split in multiple components. There's a component that has to have high privilege, and it's running the kernel, and it's KVM. But everything else that doesn't need privilege is actually moved out of the kernel, and it's residing in a different process that is called Virtual Machine Monitor, or VMM. Now, the most common VMM available today is Qemu, which is a very nice piece of software. It does a lot of things. It actually does too many things. So the problem that we have now with Qemu is that it's very complex. It does things that are not required for a VMM, and it does things that are not required for VMMs if we are targeting cloud workloads. And this is a problem because having more code in Qemu means that we have a larger surface of attack, and this means less security. So the question that we ask ourselves, and pretty much everybody in the industry is asking itself, is can we remove all the features that we don't need from Qemu and just have a small Qemu that has only what we need? And up to a couple of years ago, the answer was no, you really can't do that because Qemu is not modular. You have no way of removing the parts that you don't need. But in the past 2 years, a lot of work has been done by the Qemu maintainers to actually have a way to specialize Qemu and have a Qemu that is targeted at a very specific workload. Now, some of the reasons why this is not yet in general available distributions is because of the production cycles. So if you're running a long-term support distribution now, you probably have a Qemu from a couple of years ago, so it doesn't have these features. And the other thing is that if the distribution is general enough, it has to provide support for all the use cases of Qemu, not just the one that you or we as cloud providers need. But nevertheless, it is possible to specialized Qemu. We actually talked with Qemu maintainers, and they gave us a bunch of options that we could explore to see how much of Qemu can be actually stripped off if you are targeting cloud virtualization. And the results are very interesting. So the gray line is showing what happens to the size of the code inside the binary of Qemu when you start removing things that you don't actually need for cloud virtualization. And you can see you start with something that is almost 5 megabytes of binary code, but if you remove everything that you don't need, you could go down to less than 2.5 megabytes. So this is a huge reduction in code. And the other interesting thing is that if we look at possible alternatives today, and in this case, the most common alternative that people think about is Intel Cloud Hypervisor, which is still experimental and still doesn't have all the features of Qemu. The size of the binary is not much smaller. It's actually very comparable to Qemu. And the other interesting thing is that if we were to target a different type of workload, like micro VM, there is even more stuff that you can do with Qemu. So you could have something that's even smaller than the Qemu that have the 2.5 megabytes I was saying before. So it would seem that in terms of specialization of Qemu and reducing the surface of attack, we actually are at a good point with Qemu today. But this doesn't mean that this is everything you can do for security. First of all, the measuring surface of attack using the binary size may not be the most precise way of measuring surface of attack. Second of all, surface of attack is not everything. So we're actually working on finding new metrics to see how safe Qemu is. And the reason is, if we can't make ourselves sure that Qemu is secure, how can we convince clients and customers that it's secure? So we're looking at defect density, so, which is basically we're running static analysis over the entire Qemu code, looking for bugs that can be detected through static analysis. And even in this case, Qemu is actually doing pretty well. because the defect density of QEMU is about 0.01, and the average in the open source is 0.65. But again, this is also just a metric. Static analysis doesn't really uncover most of the CVEs and the bugs that causes CVEs in this type of applications. So what we're trying to do now is to really find which parts of the code are more sensitive to vulnerabilities. So we are looking at the CVEs of the past 4 or 5 years that were found in QEMU, and we're trying to map them to the location in the source code. And the idea that we have is that we can basically classify the code in QEMU in 3 different parts. One is the part that we removed because of specialization. And then of what's left, we believe there is a popular part of the code, which is the part of the code that is used very often in common cloud workloads, and parts of the code that are actually not that used, or maybe not used at all in these particular cases. So we're trying to classify this by using some coverage, and we're trying to map where the bugs are compared to this particular type of classification. And we already have some interesting results because we went through a bunch of CVEs, and a lot of them would actually not be exploitable at all if we had specialized QEMU, because they were in parts of the code that is not needed and not compiled if you target cloud workloads. Other are still there. So the next step we're trying to do is to see which part of QEMU is actually has actually this type of bugs. And the idea is that by being able to correlate CVEs to popular and the popular path, we believe, and we've seen other results in the industry, where what generally happens is that most of the bugs end up in the unpopular parts of the code, because those are the parts that are not really tested. And in general, the unpopular parts can be pretty big. So there's a screenshot of GCC code coverage with GCOV, and it's showing that with that particular workload, only 20% of QEMU was actually used. The rest was not used. And one of the ideas that we have is, for the parts that are unpopular, if those are really the parts that are source of vulnerabilities, we could try to add additional checks in place. We're thinking stuff like control flow integrity, to make sure that when QEMU is running those particular paths, it's actually something that it should be run, and it's not an attacker that is trying to do something malicious with the code. And the basic point there is that since this is unpopular paths, these are not used very often, so we can even take some kind of performance hit by adding more checks in those parts, because they're not very used. And that's all. So this is just a summary of the presentation.